do that. Our speaker today is Nick Wogan. He is from University of Washington in Seattle, and he's doing a lot of research and is going to talk to you today about the atmosphere of the Earth during the Hadean, Archean, and Proterozoic. He also does other cool things that he said I don't need to mention, but in this particular case, I'll let Nick take it away.
Cool. So everybody can definitely hear me, right?
Yes, sir.
Okay, just making sure. So yeah, hi everybody. Yeah, I'm a grad student at University of Washington, and I work with David Catling and also Kevin Zonley at NASA Ames, and Mark Clare, who's at St. Andrews University over in the UK. And so normally we study like the evolution of the early Earth atmosphere and use atmospheric models to understand the early Earth. But I haven't been doing that while I'm here at Goddard. I've been doing what my program at UW calls a research rotation, where in a research rotation, a student goes to another institution and does research on a topic unrelated to their PhD. So I've been working with Sean, Domo Goldman, Aki, and Chris on a project related to LUVEX. We've been looking at the detectability of methane with LUVEX. But this talk isn't about that at all. It's about the early Earth, about the stuff I do at UW. This talk is about the history of oxygen on Earth. So this plot shows the history of oxygen on Earth as we understand it right now. So during the first 2 billion years of Earth's history, during the Hadean and Archean eons, there wasn't any oxygen. And then at about 2.4 billion years ago, oxygen shot up in concentration, and that is called the Great Oxidation Event. And then during the Proterozoic Earth, so between about 2 and 1 billion years ago, there's pretty uncertain oxygen levels. And then after that, oxygen rose to near its modern level of 21% of the atmosphere. This talk is about photochemical stability of oxygen and the likely oxygen levels during the Great Oxidation Event and the Proterozoic Earth. And we'll eventually get to that. But for now, I want to tell you why the history of oxygen is important in the study of astrobiology and the study of exoplanets. One reason why the history of oxygen is important is because atmospheric oxygen permits aerobic respiration, which is the only known metabolism with sufficient energy yield that can sustain complex animal life. So this is something talked about by my advisor, David Catling, in a paper back in 2005. And yeah, so we and all the animals around us, we might owe our existence to the fact that oxygen rose billions of years ago on Earth, which is pretty wild. Another reason why the history of oxygen is important is because telescopes might try to use a spectral detection of oxygen to find life on an exoplanet. So on our atmosphere today, life produces the oxygen in our atmosphere, so it makes sense to look for oxygen elsewhere as a sign of life. An example is the LUVEX telescope. Everybody's probably, I'm sure, familiar with LUVEX. It's gonna look at Earth-sized planets orbiting sun-like stars and look at the reflected light off of those planets. And so it will be trying to take spectra that look something like this. So this is the modern Earth in reflected light. We have wavelength in microns on the x-axis and the planet to star flux ratio on the y-axis. So LUVEX will be looking for oxygen with the 0.76 micron feature shown right here. So that is all the motivation done. Back to the history of oxygen on Earth. We'll do a little bit more background. So why did oxygen rise on Earth? This is a little bit controversial, and I will not represent all the many different views on this. So take what I say with a grain of salt. But one important prerequisite to the rise of oxygen is the origin of oxygenic photosynthetic life. This happened, 3 or 2.5 billion years ago, right around there. And so this was important, but it wasn't the only important thing. There were other driving factors. So several theories suggest that the rise of oxygen was caused by a several billion year oxidation of the upper crust and mantle, possibly driven by hydrogen escape to space. So the important thing here is that, generally speaking, speaking, people think that the rise of oxygen was a very, very long-term change in the planet, in the mantle, in the crust, in the atmosphere altogether. So billions of years of evolution. So another piece of background, how do we know that the Great Oxidation Event happened? The best evidence is the geologic record of sulfur isotopes in combination with photochemical models. So here we have the record of sulfur isotopes. We have billions of years on the x-axis, so this plot covers all of Earth's history. And then we have the sulfur isotope fractionation is the y-axis. And you can see that the data change pretty dramatically at 2.4 billion years ago. And so before 2.4 billion years ago, all this crazy data, this fractionation of the isotopes, this is the mass independent fractionation of sulfur isotopes. And the cause of it is a little bit mysterious and hard to explain. And so I'm not going to give you a full explanation, but I'm going to tell you what you need to know, which is that making this signal, it requires the atmosphere photochemically generates S8, so elemental sulfur. People have modeled the photochemical production of S8 as a function of the surface oxygen concentration. And there's a pretty strong dependence. So when you don't have any oxygen in the atmosphere, you can make S8. But as you go to higher concentrations, it falls off dramatically and you can't make S8. So there comes a concentration where it's really just not possible anymore. And that's at maybe 10 to the minus 7 oxygen mixing ratio. So if we go back to the plot on the left, the disappearance of the mass independent fractionation of sulfur isotopes at 2.4 billion years ago is strong evidence that oxygen first rose above 10 to the minus 7 mixing ratio. But the story is more complicated than I have presented on the previous slide. Recently discovered data suggests sulfur mass independent fractionation turned on and off several times between 2.4 and 2.2 billion years ago. This is evidence of fluctuating oxygen levels right after the Great Oxidation Event. This is interesting because there are some papers in the literature that argue that once oxygen rose, it was an irreversible and a very stable event. So this new data goes against that paradigm. One problem is that the evidence for fluctuating oxygen levels and the stability of O2 concentrations in general have not been reconciled with atmospheric photochemical models. So let me unpack this statement in the next few slides. First of all, what is a photochemical model, a 1D photochemical model? In words, a 1D photochemical model is a description of how atmospheric chemistry changes over time from chemical reactions and vertical gas transport. And in math, a 1D photochemical model solves this system of partial differential equations. So on the left is the rate of change of a species concentration, and it changes because of chemical reactions, the two middle terms, and then vertical transport, the last term. Previous models of the Great Oxidation Event and of oxygen in general, they treat it as a photochemical equilibrium process. So I will explain to you here what I mean by photochemical equilibrium. So suppose you have an atmosphere. It's got some molecules in it like methane and oxygen and CO2. So this plot is mixing ratio versus altitude in abstract units. And let's suppose this atmosphere is at photochemical equilibrium. So that means that there are lots of reactions happening all over the atmosphere. But when you add up all the contributions of all the reactions, no molecule is changing with time. Everything balances out. And so the rate of change of oxygen in the atmosphere is 0, and the rate of change of methane in the atmosphere is 0. And the same is true for every other molecule. So hundreds of thousands of molecules in the atmosphere. So then suppose there are changing gas fluxes at the surface of the planet. This might be caused by a volcano erupting, spewing a bunch of gases into the atmosphere, or it might be caused by a change in the biosphere. Biology produces methane and oxygen, so if you mess with the biosphere, it would change those fluxes. So with changing fluxes, the atmosphere would no longer be at an equilibrium state, and it would want to change. So it would for a period of time, and it would reach a new equilibrium with different gas concentrations. So previous models, they cannot accurately resolve atmospheric transitions. They can work out what the atmosphere looks like before it starts to change and after it stops changing. But I can't figure out all the atmospheric states in between. This is a problem because the Great Oxidation Event could have been a rapid atmospheric transition, not well characterized by steady state modeling. So this motivates our solution. We made a time accurate photochemical model to investigate the time scale of the rise and fall of oxygen during the Great Oxidation Event and the stability of different oxygen concentrations. So I'll tell you very briefly how we did this. This took many months, and I will tell you how we did it in like 20 seconds. So we started with the Atmos photochem model. I think you guys are aware of this model. It's got a lot of history. It's been around for a while. It's a great model. Maintained here at Goddard and also part of the Virtual Planetary Laboratory Group. So we took that model and we changed the ODE integrator, the ordinary differential equation integrator in it, and replaced it with the CVODE BDF integrator. This is a fancy integrator from Lawrence Livermore National Laboratories. It's designed to accurately solve equations like the photochemical equations. So the addition of this fancy integrator is what allows us to accurately evolve atmospheres through time. We also implemented some Fortran 90 features. So Atmos Photochem is written in Fortran 77. So we changed some of the code to Fortran 90 practices. And then we used the Python package numpy f2py to make a Python wrapper to all the Fortran. This made a new sort of version of Atmos that we call photochempy. So you interact with the code via Python, and it can accurately evolve atmospheres with time. So here is an example model run. This is a model run of the rise of oxygen on Earth. So on the left-hand side are mixing ratios of gases as a function of altitude in the atmosphere. And on the right-hand side are photons hitting the top of the atmosphere in blue and the surface in orange. And so you're really gonna just wanna pay attention to oxygen over here, which is the blue line right here. And in this simulation, I started with an atmosphere that was at photochemical equilibrium. Then I changed the methane flux at the surface, and that's gonna change the concentration of every gas. Oh, this is a movie, yeah. And it has a slow start, so we're gonna have to wait a bit. In about 1,500 years, oxygen shoots up in concentration, and the oxygen photochemistry makes ozone. So ozone builds up. And the ozone actually shields a lot of the ultraviolet light, which we can see here. There's very little light, less than 300 nanometers hitting the surface of the planet. And then oxygen reaches a new steady state around 1% or just under 1%. So here's another look at that same simulation. So this is just zooming in on the transition. This is the surface oxygen mixing ratio as a function of time. So the surface oxygen mixing ratio is referenced to the right-hand axis. And then the gray shading are the 250 nanometer photons in the atmosphere as a function of altitude. So you can see that when oxygen rises and the ozone layer develops, it shields the lower atmosphere and casts a UV shadow on the lower atmosphere, which is pretty cool. So in the next few slides, I'm going to show you simulations just like this, where I start with atmospheres at photochemical equilibrium, and then I change the gas fluxes of methane and oxygen, and that will cause the oxygen levels to change. And methane and oxygen, they're made by biology, so these simulations might be representative of how the atmosphere changes when biology changes.
Quick question though. Obviously, like you can have biology as a source, but it's kind of agnostic in terms of like, well, what could have actually put that in there? I know there have been papers on the initiation of plate tectonics, kind of mentioned volcanism. Is that a potential, I don't know, trigger event that can be influencing these types of fluxes of the surface as well?
Yeah, so I'll get to that eventually.
Gotcha.
Yeah. No worries. Yeah. But yeah, that's a good question for later. Yeah. So the first result is that the rise of oxygen above non-negligible concentrations takes hundreds to tens of thousands of years. So this is two n-member simulations. On the left, oxygen, the blue line, rises in like 3,000 years. And then on the right, in this simulation, oxygen rises in about 60,000 years. The time scale of the rise of oxygen is controlled by the initial reservoir of methane. So if you have more initial methane, then the time scale is longer. So the reason why this makes sense is because when you have, so oxygen can't rise when you have a bunch of methane in the atmosphere, because the methane, means that there's lots of reducing gases in the atmosphere. And so the photochemical destruction rate of oxygen is really big. So it just can't rise in concentration. So you need to deplete the whole reservoir of methane before the O2 can rise. And so if you have a bigger reservoir of methane at the beginning, it's just going to take longer to deplete that big reservoir. So it's very simple. So on the right here, we start with a big reservoir of methane, and it just takes a while to deplete that big reservoir. And on the left, we start with a smaller reservoir of methane. It just takes longer or a shorter amount of time to deplete the reservoir to allow oxygen to rise. So the second result is that reversing the transition takes about the same amount of time. So removing the oxygen in the atmosphere takes about the same amount of time. We have two more simulations demonstrating that. So on the left, oxygen falls out of the atmosphere in about 100 years. And on the right, oxygen falls out of the atmosphere in maybe 40,000 years. The time scale of the fall of oxygen is controlled by the initial reservoir of oxygen. If you have more initial oxygen, then that's a longer time scale. This is very simple. If you have more oxygen, then it just takes longer to deplete. So on the right, we start with a lot of oxygen, so it takes a long time to deplete it. And on the left, we start with a lot less, so it takes less time to deplete. So here's a summary of the last few slides. When methane is big, O2 changes slowly. It's stable. When oxygen is big, then O2 changes slowly. It's stable. But when oxygen and methane are small, O2 is prone to very rapid change. It's unstable. So I want you to remember this little summary here, and we will briefly look at a different plot. So this is a plot of many, many photochemical equilibrium calculations. Each dot is a different simulation where I've taken an atmosphere and run it to an equilibrium state where nothing is changing anymore. And this is over a pretty big parameter space. So we're considering, the different sorts of uncertainties and fluxes and so forth for the early Earth during the Great Oxidation Event. And there's a few different regimes that I want to look at in terms of our conclusions at the top of the slide. So first, let's consider small oxygen concentrations below 10 to the minus 8 mixing ratio. Well, in this case, there's not many oxidizing gases in the atmosphere. And so that means methane can rise to high concentrations, as we can see in this plot. So this is, methane, oxygen mixing ratio versus the methane mixing ratio. So methane can rise to high values. So when you have a lot of methane, that makes oxygen stable. And then let's consider high oxygen levels, so above 10 to the minus 4 mixing ratio. Well, in that case, there's just a lot of oxygen in the atmosphere. So when you have a lot of oxygen, that makes O2 stable. But then there's a middle ground where oxygen and methane are annihilating each other in the atmosphere almost perfectly. And you don't have that much oxygen and you don't have that much methane. So there's a region where there's no very little oxygen and methane, and that makes oxygen unstable. So I want to look at these different regimes more carefully with some time-dependent photochemical models. So let's first consider the small oxygen regime, oxygen below 10 to the minus 8 mixing ratio. So here we have a time-dependent photochemical model. The atmosphere starts at equilibrium with just under 10 to the minus 8 O2 mixing ratio, the blue line. And then I impose an oscillating methane flux. This is about a 25% oscillation in the methane flux. And you can see that oxygen is stable. It doesn't change over time despite this big changing flux. Then we can consider the big oxygen case with a similar time-dependent photochemical model. Here I start with an atmosphere that has just above 10 to the minus 4 oxygen mixing ratio and impose the same methane flux variation. And oxygen is again stable. It wiggles a little bit, but it doesn't wiggle that much. And then we can run, another simulation for this middle scenario for oxygen between 10 to the minus 8 and 10 to the minus 4 O2 mixing ratio. And this time, we start with oxygen at 10 to the minus 7 mixing ratio and impose a very small oscillation in the methane flux. So this is just a 5% variation. And this causes oxygen to vary by 4 orders of magnitude, by a very large amount. And so, these time-dependent models seem to pan out with our interpretation here. There appears to be a range of oxygen concentrations between maybe 10 to the minus 8 to 10 to the minus 4 O2 mixing ratio that are unstable to perturbations in surface fluxes. So yeah, the claim. There are a range of O2 levels between about 10 to the minus 8 to 10 to the minus 4 O2 mixing ratio that are unstable to relatively small perturbations in surface gas fluxes. So a crucial part of this claim is that there must be perturbations to cause O2 to be unstable. And in the previous slide, I imposed methane flux perturbations, but I gave absolutely no justification for their existence in the real world. And so we need to answer this question. Do perturbations in surface gas fluxes occur on Earth with timescales and magnitudes that can cause 10 to the minus 8 to 10 to the minus 4 O2 mixing ratio to be unstable? Well, we can start with the methane flux variations in recent Earth history from ice core data. That's shown by this plot right here. So this is the thousands of years ago on the x-axis, and then the methane flux is the orange line. So you can see that maybe 20, 30, 40% change. The methane flux has changed by maybe 20 to 40% over the past 800,000 years. This is actually caused by ice ages. So during a warm period, there's lots of wetlands. Wetlands are a major source of methane to the atmosphere. So during a warm period, there's wetlands on land, and so there's a big methane flux. And then during an ice age, the ice advances and the wetlands get covered, and there's a smaller methane flux. And so all these wiggles in this plot here, it's actually just ice ages coming and going. So the ice advances over land and it covers wetlands, and there's a small methane flux. It retreats, and there's a big methane flux, and that just happens over and over again. And the periodicity of this, like the time scale that these oscillations happen, it's linked to Milankovitch cycles. So the Earth's orbit has little wiggles in it, or wiggles in the eccentricity and the obliquity, and those ultimately drive ice ages occurring, which ultimately drive variations in the methane flux. So one problem is that we're talking about the Earth 2 billion years ago, and there would not be wetlands back then because plants are in wetlands, and there's no plants 2 billion years ago. But methane flux variations on the early Earth from a similar process involving microbial mats is conceivable. So there's this paper by Zhao and others, and they did some experiments and modeled microbial mats on Proterozoic land, and they found that these mats could be a substantial methane source to the atmosphere. So these microbial mats could possibly be completely analogous to wetlands, where you could have ice advancing over land, covering microbial mats, reducing the methane flux, and then that ice could retreat, and the methane flux would increase as the microbial mats came back. And so here is a simulation I already showed you, but this is where I have oscillated the methane flux by 5% over Milankovitch timescales. So this is an oscillation with a 10,000 year period. And just this 5% variation in the methane flux causes big fluctuations in oxygen between 10 to the minus 8 to 10 to the minus 4 mixing ratio. And then another possible thing that could cause changing methane fluxes or changing surface fluxes are really big volcanic eruptions called large igneous province volcanic eruptions. So geologists have gone out and they've looked at the early Earth stratigraphy, and they've identified that there were quite a few extremely massive volcanic eruptions that occurred right around the time of the Great Oxidation Event. And so on the right here, I have a simulation, photochemical simulation, where I start with an atmosphere at equilibrium, photochemical equilibrium. It is just above 10 to the minus 5 O2 mixing ratio. And then at time equals 0, I impose surface fluxes of hydrogen and CO representative of a large igneous province volcanic eruption. And it depletes all the oxygen in the atmosphere in about 100 years. So you can imagine that, on the early Earth, there'd be periodically volcanic eruptions that could substantially vary these oxygen levels.
Nick?
Oh, yeah.
Yeah, quick question. I didn't mean to interrupt, but you have this on all your figures, the O2 mixing ratio. So is the, in all the simulation, do you prescribe O2 mixing ratio, or do you prescribe oxygen flux? Or do you keep the oxygen flux fixed?
The flux is prescribed and the mixing ratio is calculated.
So you kept, so O2 flux is kept throughout at the fixed ratio, varying methane by a little bit, like in the previous figures, right? Is that correct?
So I am not prescribing any surface concentration. I'm prescribing only surface fluxes.
Yeah, that's what I said. So you have a surface oxygen flux O2, which you keep fixed, and then you have this sinus function of CH4 on the previous figures. Is that right?
Yeah.
For methane, right?
Yeah. So in this figure, the methane flux is being varied. Yeah.
But an oxygen flux is being kept fixed throughout the transition.
Correct. Yeah.
Yeah. Gotcha. Thank you.
This is John Cooper. I have another question.
Was that?
This is John Cooper. I have a question.
Oh, yeah.
It doesn't look like you're considering any kind of buffering effect by water ocean. Of course, there's a lot of water, in fact, liquid or ice. So might that impact this in some way? If there's a buffering effect by the oceans for dissolved CO2 or things like that.
So yeah, what would matter is the reservoir of reducing species in the ocean. And so if you could have a lot of, say you could dissolve a massive amount of oxygen in the ocean, then that would, serve as a buffer, sort of a redox buffer. Or if you could dissolve a lot of reducing gases from the atmosphere into the ocean, then that would be a buffer, So in either case, that would be a buffer. And so when you try to estimate that using the solubilities of various gases, really the oxygen can't hold that many reducing or oxidizing gases relative to the atmosphere. But then there's longer timescale buffers. So the crust, for example, has lots of reducing or oxidizing species in it, but the equilibration between the atmosphere and the crust is over very long timescales, like the timescale of plate tectonics. So we think it's reasonable to assume that they're effectively uncoupled over the 10 or 100,000 years that we're modeling here. So yeah, there are lots of reservoirs at play, but for these simulations, it's the atmosphere and ocean is what we think it's reasonable to consider just those. That makes sense.
Okay, thank you.
Yeah. So yeah, I want to just return to the question I started with a few slides ago. Do perturbations in surface gas fluxes occur on Earth with timescales and magnitudes that can cause 10 to the minus 8 to 10 to the minus 4 O2 mixing ratio to be unstable? And I think the answer is probably yes. So I gave two examples. Perhaps you could have ice advancing and retreating over microbial mats, changing the methane flux by a small amount. And maybe you could have volcanic eruptions, which we know happened. Those volcanic eruptions would push reducing gases into the atmosphere and change O2 levels. So let's go back to our plot of O2 through history and apply what we've learned. So the first thing is, here's our unstable oxygen region between 10 to the minus 8 to 10 to the minus 4 mixing ratio. So the first conclusion is that our modeling is consistent with geologic evidence of O2 oscillations during the Great Oxidation Event. So we imagine them when oxygen first rose, it was in this unstable region. And every once in a while, a change in the biosphere or a change in volcanic outgassing caused big variations in O2 levels. And that's why we see evidence for it in the geologic record. And then the second main takeaway has to do with the longer term record of sulfur isotopes. So this is the plot I showed you before of the sulfur isotope fractionation through all of Earth's history. So if we look at the isotopes between 2 and 1 billion years ago, so that's the Proterozoic eon, there isn't any isotope fractionation. So the lack of sulfur mass independent fractionation during the Proterozoic eon means that O2 never collapsed below 10 to the minus 7 mixing ratio. So according to the sulfur isotopes, O2 never fell below this line right here, this dotted line, during the Proterozoic eon. But suppose oxygen was just a bit above 10 to the minus 7. Suppose it was at 10 to the minus 5. Or, well, our modeling results, they say that this is not a stable O2 level to be occupied at for billions of years. Every once in a while, a change in the biosphere or a volcanic eruption would cause significant variations in the O2 levels. So you would expect O2 to occasionally drop below this threshold of 10 to the minus 7. But according to the geologic record, that never happened. So really the conclusion is that O2 had to be above 10 to the minus 4 mixing ratio for stability. Just to put it all together, our modeling and the lack of sulfur mass independent fractionation suggests that oxygen was above 10 to the minus 4 on the Proterozoic Earth. So yeah, this is really what I want you to take away from the whole talk. So I have no summary slide. This is the summary. So thank you for listening.
Interesting stuff, Nick. I'll let people online, can you go ahead and raise your hand first so that we can have a, not like a free for all question? Because I'm sure I've always seen a bunch. So Sean, I see your hand up went up immediately, so go for it. And then Mike, I see you had a question in the chat, so you will be next.
We can go to Mike's question first if you want to read it, Prabal.
Okay, sure. I'll go ahead and read. Mike, do you want to go ask the question? You can elaborate beyond.
I think it's pretty straightforward, but it seems to me that you're implying these large reducing gases from these lips, but lips are extremely common throughout Earth history. And it seems to me what you're saying is you need sort of a quiescent period to keep, to keep this kind of thing from happening as the oxygen's rising over time. Isn't that what you're saying, basically?
So you need a quiescent period where there's no volcanic, or say that one more time.
You need a quiescent period where there are very few or no lips going off to keep this oxygen from acting this way, basically, from being so variable.
Yeah, it's hard to, because there's very long-term drivers of oxygen, right? There's like big long-term oxidation of the crust and mantle, and that is overlaid this, shorter term stuff that I'm talking about. Right? I'm talking about 1,000-year changes, 100 to 1,000-year changes. And so, maybe, so these oscillations that we see right after the Great Oxidation Event, maybe this was a period where there was longer term drivers. So this is like 200 million years. Maybe there was, long-term drivers that just caused oxygen to sort of waver in this unstable region for a period. But then, eventually, hydrogen escape or whatever mechanism you want to posit that oxidizes a planet, that pushed us into a threshold where oxygen was a bit higher and everything was a bit more stable. So, there's, a couple different timescales of process.
Okay, no worries. Thanks.
Yeah.
So it looks like we have multiple other people. Let's go with hands right now, just because otherwise it's a little confusing. But there's in the reactions section on the bottom, there's a raise hand feature. So if you have a question, feel free to click on that. Sean, go ahead.
I have like 10 questions, but I'm only going to ask, I think, one for now. I'll come back with others later if other people ask theirs. So Nick, you're saying that there's a lack of sulfur MIF in the Proterozoic. I haven't looked at the data in a long time, like a decade. My recollection was that there was a brief little blip of sulfur MIF around the snowball Earth events towards the end of the Proterozoic. Am I remembering that wrong?
maybe there could be. I guess, I mean, this is, I guess, the main data that I have looked at. I don't think there's anything as significant as what was,
No,
still fractionation
yeah.
significant, but maybe there's smaller amounts of fractionation that has been resolved. And
Yeah,
yeah,
it was nothing like the spread we saw in the Archean.
okay, yeah. I'm not
Um,
honestly not familiar at all with the sort of the 1 billion year ago, like the neoproterozoic snowballer stuff. Is that what you're talking about?
yeah, yeah.
Yeah.
Maybe I'll ask one other quick one, which is, have you looked at whiffs of oxygen, and have you looked at like how big of a whiff can you get? And does it reconcile some of the things that people have been talking about in that literature prior to the rise of oxygen?
Just really quickly, do you mind acronymizing some of the stuff you and Sean are talking about?
Oh,
Okay.
Oh, sorry.
Fractionation, stuff like that.
Apologies.
No
yeah,
worries.
yeah. So yeah, the whiff. So yeah, going back to this plot here of oxygen, like one thing I should have put actually on this plot is that there's evidence in the geologic record that there were, quote, whiffs of oxygen where like, there's various data that suggests that maybe, there's a little bit more oxygen in the atmosphere just prior to the GOE. And yeah, Sean's asking if like, what does this say? What does this work say about that? So it does, I don't think it says that much about it because it's hard. Well, it's it's something we haven't looked at too carefully, but it's hard to make like a true whiff of oxygen in that, like, even when oxygen, or especially when oxygen is pretty low in concentration, the methane sort of gets high enough and there's enough reducing gases that there's enough inertia in the atmosphere, enough chemical inertia, that it's hard to imagine any forcing that would cause a whiff. And so it's a little bit mysterious to me, honestly, how those cropped up and what they actually mean in terms of like the O2 levels in the atmosphere. So yeah, a summary is, I don't know, actually. Yeah.
I agree with your take for what it's worth.
Okay.
We could talk more about it later. I think there might be something going on in the ocean chemistry with the equivalent oxygen fugacity, but not literal oxygen in the atmosphere.
Okay. Yeah, it would be great to talk about that, actually. Yeah.
Alex?
Yeah, so before I forget, the problem mass independent fractionation you're talking about, Sean, that was in oxygen isotopes. That's all the reports I heard about a decade ago during snowball. But back to the talk. So ultimately, regardless of the solver, the abundance of oxygen, how high it is in the atmosphere, is dependent on the disbalance of fluxes of reductants versus oxygen into the atmosphere.
Yeah.
And the transition which you showed, essentially, like whenever you have oscillations of oxygen, is indicative that you have bistability of oxygen in the atmosphere when the fluxes of reductants and oxygen are about even. This result kind of was around for a while. Kevin had it, I had it, and there was also a Nature paper which was claiming this actually with some semi-empirical evidence.
Yeah.
So when you have essentially two stable solutions, when the flux of reductants is about the same as flux of oxygen, and you can, with a small perturbations, small disbalances, can jump between these two solutions. So that's what I think what we observe as well through your presentation. So this is very consistent. The question I have though is, if this is the explanation for oscillations of sulfur mass independent fractionation throughout hundreds of millions of years in a kind of late Archean, then what is your current view on how can a system persist in such a state when the fluxes of reductants and oxidants would be about even, but not in a substantial disbalance? Because that's what ultimately will control the duration of that transitional period, which from geology, based on sulfur isotopes, looks like very long. But hundreds of millions of years, that's a long time. You know, atmosphere can fill very quickly. So would like to know your thoughts on that.
Yeah, I guess like, yeah, I think my thoughts are, I already said this sort of, but I'll just say it again, is that I do imagine in the background here, there are very long-term forcings of oxygen in the atmosphere, like oxidation, you know. So like an example is right, hydrogen escape. It's happening very, very slowly. It's a multi-billion year thing or 100 million year thing. And so it's moving the planet in a direction in terms of its oxidation state. And that is interfacing over all of the high frequency stuff that happens, like volcanic eruptions and, you know, changes the biosphere, and all the, you know, the atmosphere can change super fast. And so I guess that is how I view this long period of instability that we have in, you know, right after the GOE, is really you needed to, the long-term forcing is what needed to push the atmosphere into a more, you know, oxidized state that was stable. But as it was slowly making its way there over, you know, 200 million years, there's all this high frequency stuff happening, which causes oxygen to, you know, go all over the place. So that's how I view it. I don't know if that makes sense. I don't know.
Well, the hydrogen, we can talk longer on the other people obviously speak on this, but hydrogen escape or some slow changes of the oxidation state, you can attribute this to very early, you know, but once you're, you know, in a diffusion limited escape, I mean, we know the rates of at which hydrogen is escaping, you know, so to explain how you can persist in that you know, state where you can, you know, your fluxes are balanced, oxygen with reductants. Yeah, that's tough to do with hydrogen escape. We can talk offline.
Yeah, hydrogen escape, or, you know, whatever other theory, changes in the oxidation state of the mantles, you know, slowly over 200 million years, or, you know, so, you know, you can pick your favorite cause of the GOE. Any sort of long-term forcing is what I'm imagining. But yeah, it would be great to talk about that.
So really quickly, we have more hands up. I did get scrolled the comments. So Jessica and Hayang, I think you both had questions. Do you want to ask them, or I can just read them off? If you would like to, you can unmute yourself and ask them. Otherwise, we also have a lot of hands up, so we only technically have till 2. So I might give Nick's email out so that you can talk to him, because there's clearly a lot of interest in this work. But let me go and see what. All right, so I'll actually just read off some of these questions. The first one is, in addition to other potential kind of things that might be considered, people mentioned about a water buffer. How about additional buffers such as CO2? How would that change the rate of, you know, oxygen over time?
I thought it would matter. I thought CO2 would matter, but I've done all these simulations with a bunch of different CO2 concentrations, and it doesn't seem to matter. And I guess the reason it's just sort of a redox neutral species. So really what matters here are, you know, some of us have become used to speaking in terms of redox, and other people are like, wow, that's like the most confusing language ever. But I will speak about it anyway. Yeah, what matters for this story is, you know, if you got methane versus, you know, O2 versus hydrogen, you know, it's the extremes of the redox spectrum and the reservoirs of those gases. And so since CO2 is redox neutral relative to those extremes, it doesn't play a huge effect.
And the other question I see in the chat is, it's not a dumb question for sure. How large does an eruption need to be called a large igneous province? And really beyond that, you know, really cause some of these variations that you have this maybe secular increase in oxygen?
Yeah. So large igneous provinces are like really special massive volcanic eruptions. So we have one that happened 18 million years ago in Washington, Columbia River flood basalt. As like the Yellowstone hotspot moving through Oregon, basically. It used to be in Oregon, turns out. So that happens every 40 million years. There's one really, really massive volcanic eruption, a large igneous province. And so then each of those big, large igneous provinces, those last for a while, like millions of years. And then within each of those, there are multiple big eruptions that happen. And it's like those big high volume eruptions are what is required to make enough gases that significantly affect the atmosphere. So you can't be just any old volcano, right? It has to be the biggest eruptions that have ever occurred on Earth. So yeah.
Thanks. And so what we'll do is, because we're running kind of close to time, I'll go ahead and take questions from the hands I see that have not asked. So Avi, go ahead.
Yeah, Nick, great talk. Really, really interesting stuff here. Obviously, a lot of unknowns for very rapid changes in factors, and you kind of have like one metric, the sulfur isotopes, and then of course you could look for evidence of lips and things. But I guess I'm saying, how do you break a lot of these degeneracies, like the actual rates of O2 or CH4 or other, you know, chemical factors? Are there other things that we could compare over this time scale to try to break some of these?
Yeah, I think like the key is really like looking at the, you know, being creative about what's in the geologic history, what's in the data. And yeah, I mean, you know, we focus on sulfur mass independent fractionation because it's like the thing for oxygen, but there's other redox sensitive elements. And there's actually a paper that came out, and it talks about how they find Milankovitch cycle variations in redox sensitive elements on the early Earth. So they see that there perhaps is some variation in the redox state lining up with Milankovitch cycles, which is really interesting. But that is, the problem is with that data, it's like, it's much harder to interpret than the sulfur mass dependent fractionation stuff. So I think the key is maybe different sources of data, if we can better understand like redox sensitive elements and what they actually mean for O2 levels. But I know that's hard. So yeah.
Just to add a kind of like fun thing that I think might scare some of the people on this call. Like, remember, this is the Earth. So actually like cyanobacteria, like DNA, and doing genetic, you know, analysis of that over these periods has been, there have been papers on that try to reconstruct kind of oxygen presence and variation over time. So they actually get living things to work with, which is kind of cool, you know. But Vlad, I think you're next.
Thanks for an interesting talk. So yeah, my question is about atmospheric pressure. So we know that atmospheric pressure on Earth, you know, 2.5 billion years, well, at around that time, right, was lower than it's today. So at least half, if not 1/4. That's the first thing. The second thing, we know that you know, extreme UV flux was also greater, at least by 50%, if not by a factor of 2. Yeah. So that will enhance the photodissociation of carbon dioxide. Yep. And probably change some of the, you know, chemistry. Have you studied those sensitivities to those parameters?
Yes, I have studied the sensitivity to the UV flux. So yeah, all these simulations are for an estimation of what the UV flux was way back when. And then I have basically just done all these simulations for Earth at different periods of time, you know, 4 billion years ago, or 2 billion years ago, or 1 billion years ago. And it doesn't really matter for the UV flux. For the surface pressure, I have not done those simulations. I think basically what is going to happen is it's going to change the reservoir of reducing gases in the atmosphere. If you have less atmosphere, that means smaller reservoirs, which changes the timescales by, you know, the relevant factor. So if you have half atmosphere, you know, half a bar compared to 1, I did all these simulations at 1 bar. But if you have half a bar, then all these time scales will probably be halved by about, you know, by 1/2. And so that's the dependence that I expect. Yeah.
But the point is that if you have, let's say, 1/4 of the atmospheric pressure, then you can start dissociating CO2 and create a lot of, you know, free oxygen somewhere in the, you know, upper troposphere. So because of the lower, you know, the column density. So, and that will change probably the whole chemistry.
It will, but I mean, CO2 again is redox neutral. And so when you dissociate the CO2, you get the O2, but you also get the C. And so, and in terms of how oxygen changes, what matters is, imbalances in redox species. So, maybe it would matter. I'm not really sure the magnitude of its effect. But I think what would matter more is if there was a change in, actual redox that could be caused by, something. But yeah, I don't know. It's worth thinking about and doing a simulation. Yeah.
Yeah, because you have only one sink through the H2O basically for the CO.
The CO, H2O.
Yeah.
Oh yeah.
But let's, so we're actually coming up on that 2 p.m. Dylan, I know we still have hands because this is really interesting, thought-provoking talk. What I'm going to do is I'm going to let, I think Nick's email address is on the invitation, so you can email him questions that I'm guessing you're okay with answering those offline. And I know that we have a hand up here too, but what I'll do is I'll let you basically talk to Nick after this just to make sure we're not taking up the room or anything else after that. But thank you so much, Nick. This was super interesting, and I think we all had a bunch of really thought-provoking stuff. Thanks.
Yeah, thank you guys so much. It's really, really fun. Yeah.
Great talk. Thanks, Nick.